In this video, we applied the Rayleigh Ritz method with tent functions to find an approximate solution to the boundary value problem given by the differential equation y double prime plus 0.5 y prime minus y equals e raised to the minus 0.4x power times cosine 4x with the boundary conditions y of 0 equals 0 and y of pi equals 0. We will write a Mathematica code for the computation of the coefficients of the approximate solution. We had derived formulas for the Rayleigh Ritz method with tent functions in another video whose title is the Rayleigh Ritz method and tent functions getting ready to write a code. We are including a link to this video in the description of this video lecture. We partitioned the interval from 0 to pi using a uniform partition with the n plus 2 nodes x sub 0 to x sub n plus 1 so that the step size h, or the length of each subinterval, will be pi over n plus 1. Then x sub I will be equal to I times h for I equal to 0 to n plus 1. The ith tent function phi sub I, whose peak is at x equals x sub I, is given by this formula. Let phi of x be the resulting approximate solution so that phi of x equals the sum of the product of c sub I and phi sub I, where the c sub i's form the vector c and satisfy the equation the matrix R times the vector c equals the vector S. R is a tridiagonal matrix with only the entries R sub I, R sub I minus 1, and R sub I plus 1 being the only possible non-zero entries. We wrote these formulas for R sub I, R sub I minus 1, and R sub I plus 1 in the video The Rayleigh Ritz method and tent functions getting ready to write a code. S is a vector whose components we had designated as lowercase s sub I. And we had s sub I equal to a sub 5I plus a sub 6I for I equal to 1 to n. In the same video, we also had these formulas for a sub 1I, a sub 2I, a sub 3I, a sub 4I, a sub 5I, and a sub 6I. Before we start the code, we convert the differential equation into this form. We multiply everything by the integrating factor e raised to the 0.5x power, 0.5x being an antiderivative of 0.5. The product rule in reverse transforms the derivative terms into the derivative of the product of e raised to the 0.5x power and y prime, and then we have the rest of the equation. Then we change the sign of every term. So p of x equals e raised to the 0.5x power. Q of x is also e raised to the 0.5x power. And f of x equals minus e raised to the 0.1x power times cosine 4x. For the trial run of the code, we set n, the number of tent functions, equal to 10. The step size h is pi over n plus 1. We use a do loop for the x nodes. The ith x node, or x node sub I, equals I times h, with I going from 0 to n plus 1. We use a do loop to define each uppercase A. A sub 1I equals an integral, so our first impulse is to use the integrate command. But for some reason, Mathematica sometimes switches to the polar form of complex numbers when dealing with exponentials and floating point. Then, Mathematica often includes infinitesimal imaginary numbers which are supposedly zero when everything is simplified. But unsimplified, these infinitesimal imaginary values screw things up, such as when we plot graphs of functions. So we use the numerical integration command n-integrate. We n-integrate p of x. We will factor out 1 over h squared from the integral so that we n-integrate p of x from the I minus 1th x node to the ith x node. Then we divide by h squared. I goes from 1 to n plus 1. a sub 2I equals n integrate of the quantity x minus the I minus 1th x node, or x node sub I minus 1, the whole thing squared, times q of x, and again we factor out 1 over h squared. X goes from x node sub I minus 1 to x node sub I goes from 1 to n. Here's a sub 3I. Here's a sub 4I. Here's a sub 5I. And here's a sub 6I. We now define the non-zero entries of the matrix R. R sub I equals a sub 1I plus a sub 1I plus 1 plus a sub 2I plus a sub 3I, with I going from 1 to n. R sub I minus 1 equals minus a sub 1I plus a sub 4I, with I going from 2 to n. R sub I plus 1 equals minus a sub 1I plus 1 plus a sub 4I plus 1, with I going from 1 to n minus 1. S sub I equals a sub 5I plus a sub 6I, with I going from 1 to n. To input the matrix R, we use nested tables and nested if statements. For the diagonal entries when I equals j, then the entry is simply R sub I. If it is the entry to the left of the diagonal, then the column number j equals I minus 1, and the entry is R sub I minus 1. If it is the entry to the right of the diagonal, then j equals I plus 1, and the entry is R sub I plus 1. All the other entries are 0. J goes from 1 to n, and I goes from 1 to n. For the vector s, we first form the table or list of the s sub i's, with I going from 1 to n. We then enclose this list within a pair of curly brackets to form a row vector. Then we use the transpose command to get s as a column vector. Since uppercase C is a special character for Mathematica, we'll call the vector of the C sub i's uppercase double C, or CC. CC equals the inverse of the matrix R times the vector S. We use a do loop to extract each C sub I from the vector CC. C sub I equals CC sub I. The index I indicates the row number, then comma 1. The index 1 is for the first and only entry of each row of CC. We now input the tent functions. We write the ith tent function as phi square bracket I underscore square bracket x underscore square bracket. This is a format that works for defining subscripted functions such as phi sub I, so that we are also defining the index I as a variable. We also have to use a colon when defining phi sub I because we will be using an if statement to define each phi sub I. Using an if statement for defining a function often requires delaying evaluating the function. The colon does precisely that. We will not need to evaluate any of the phi sub i's until we sketch the graph of the approximate solution. So, if x is less than or equal to x node sub I minus 1, phi sub I of x is 0. But if x node sub I minus 1 is less than x, which is less than or equal to x node sub I, then phi sub I of x is the quantity x minus x node sub I minus 1 over h. And if x node sub I is less than x, which is less than or equal to x node sub I plus 1, then phi sub I of x is the quantity x node sub I plus 1 minus x over h. For all other values of x, phi sub I of x is 0. Since we are using the variable phi for the phi sub i's, we call the approximate solution g of x. To define g of x, we use colon equals the sum of c sub I times phi sub I of x. We are using the colon again because of the conditional if statements in each phi sub I definition. We plot the graph of g for x between 0 and pi. We also specify the plot range to be between minus 0.1 and 0.1. We execute all the lines of code and obtain the polygonal graph of the approximate solution that is a piecewise continuous function. Let's increase n to 100 and execute the lines of code. Gaps in the graph of piecewise functions sometimes happens with Mathematica. To remedy this, we increase the initial number of sample points plotted before adaptive refinement to 100 by specifying plot points 100 and execute the code. The boundary value problem can be solved for exactly by finding the general solution to the differential equation y double prime plus 0.5y prime minus y equals e raised to the minus 0.4x power times cosine 4x, and then solving for the particular solution using the boundary conditions. This allows us to compare the approximate solution to the exact solution, which is shown as the wider curve drawn in yellow.